Welcome to probability. Today we're going to be talking about Markov chain, and we'll be using the expansion theorem. The Markov chain starts with a single row matrix. Each entry, with each entry, the probability of starting in a state. Next comes a transition matrix, where the entries are the conditional probabilities of going from one state to another, or staying in a state. When a row matrix is multiplied by a column of the uh, transition matrix, an expansion occurs. So we do this using each column, and we end up with a result being an output matrix, which is a probability space as well. So what does all that mean? It's best to go ahead and just illustrate it. Suppose we have something that has three states: 1, 2, and 3. The probability, if it starts in state 1, that it goes to state 1, the conditional probability, it's here. What if it starts in state 2 and goes to state 1? That's this probability. Given it starts in state 3 and goes to state 1, it's this probability. Now, it could start in state 1 and go to state 2. It could start in state 2 and stay in state 2. It could start in state 3 and stay in state 3, and so on. And these would be the probabilities of it ending up in state 3. So we end up with a probability space. This looks like this, but these are at different times. This is after the transition. This is before the transition. So there'll be different numbers. The row matrix that results here in blue is going to come from the probability of S1 times the probability of S1 given S1, plus the probability of S2, probability of S1 given S2, and the probability of S3, the probability of S1 given S3. So that's really an expansion theorem for the probability of S1. Right here, S1, that's where we end up. And these are, so this is the expansion for ending up in S2. And this is the expansion for ending up in S3. And so we take this column, we get the first, which is here. This times the second column, this expansion, which is here. And the third is here. So let's take an example. The probabilities a system is in states 1 and 2 is given by the row matrix decimal 2 and decimal 8. I put the trailing zeros so that I could work with this freely and not worry about having the numbers get too far off with significant digits. So we can assume that we can go out to 3, and we're going to have to add things to get to 1 with probability spaces, and being off in the 10,000th isn't really an issue. If the system is in state 1, the probability it stays in state 1 if the 1 transition is decimal 4. And the probability goes to state 2 if the 1 transition is decimal 6. If the system is in state 2, the probability it goes to state 1 if the 1 transition is 0.7, and the probability it goes back into state 2 if the 1 transition is 0.3. Find the probabilities of the system being in states 1 and 2 if the 1 transition. Okay, so we have a simple one with only two states. And here are the probabilities, and here are the transitions. The 100 is the 600, the 700, and the 300, all with decimals in front of them. Okay, so if I do this multiplication, I end up with a new probability space of 0.64 times 0.36. Now, if I wanted to find out after two transitions, so what is a transition? It might be a time unit, it might be an event. Uh, we look at this group of states transforming when something happens. It might be uh, anything you want. But we might want to repeat the experiment over and over. Maybe we apply the transition matrix and we like our results, but we better, but we don't really like them. So we're going to impact that transition matrix again and again and again until we're happy. So we can apply this technique more than once using the output from each transition as the input for the next. Now, some Markov chains reach a steady state where the probabilities of being in various states remains constant. The steady state is found by using unknowns in the probability matrix and solving for the variables that make the output matrix the same as the input matrix. So I'll show you an example of how that works. We will have to use the property that the input and output matrices are probability spaces, so the entries must sum to 1. So we're going to take some general input matrix, T and 1 minus T, can all agree that adds to 1, and impact it on our transition matrix. And let's see what happens. So we have decimal 4 times T plus decimal 7 times 1 minus T, which is decimal 7 minus decimal 7T. The second column gives us T acting on 0.6 is 0.6T, and 1 minus T acting on decimal 3 is decimal 3 minus decimal 3T. Now, if I collect like terms, the T's, negative decimal 7 and decimal 4 is negative decimal 3T plus decimal 7. The other entry will have decimal 6 minus decimal 3 is decimal 3T plus decimal 3. So we're going to end up with a system of equations. And the way we're going to end up with that, in this case, we're going to end up with a linear equation. What makes it a system of equations is that T and 1 minus T must add up to 1. We would be solving something a lot more difficult than a linear equation if we have multiple additional states. But here what we can do is take this T, the first entry, and if it's a steady state, it's going to have to equal negative 0.3T plus 0.7. And 1 minus T is going to have to equal decimal 3T plus decimal 3. So solving this equation, I can find t, and t is 0.538. I can plug that in to 1 minus t and find out what this entry is 0.462, or I could solve this equation if I wish. So when our state reaches 0.538, 0.462 matrix, state matrix, I can run that through a transition. I'm going to get the same thing out. And if I run through 100 times, it's going to have to keep on giving me the same thing. So I have found the steady state. When I get there, performing the operation, whatever it might have been, it is not going to change anything. Well, I hope you enjoyed the video, and I would appreciate if you would hit the subscribe button. I have other videos in math and multiple fields of math, calculus, algebra, trig, probability, so on. And if there's a topic you would like me to cover, you can send a comment and I will try to find the time and add it. I don't guarantee it, but I will try to see if I have the time to add it. Thank you.